It's that magical time again. It's time for chemistry. Woo! Okay, you guys apparently had this daily problem, which I didn't remember putting up. What are we looking for in this problem? Yep, we're looking for grams of hydrochloric acid. Is that the only thing we're searching for?
Concentration.
Yeah, we're looking for concentration later. Okay, tell me important information. Yep, of the base, right? Any other important information that we got up here? Yep, 50 milliliters. Anything else that we're going to need to use? Yep, hydrochloric acid. Okay, I think that's everything of value we can get out of the words here. Where do you suggest we start? Yeah. Yeah, so let's write out a molecular equation. We have to have reactants and products, right? Tell me a reactant, anybody. Okay, hydrochloric acid formula for hydrochloric acid? Yup. Aqueous. What else do we got? Okay, can you tell me the formula for calcium hydroxide? Like this? Yeah, that's what we want. Okay, that's also aqueous. They react, when you react a strong acid and a strong base with one another, what are your products? Yep, water, so we gotta have water, and then what else? Yeah, salt, so what's the salt's identity in this case? Yep. Okay, is that balanced? No, where do you want to put a 1? Which one do you like the least? Calcium hydroxide? Okay, if we go with a 1 here, we have to balance our calciums. What's got to go here? Okay, balance chlorines. What's got to go here? Up. And then finally, let's balance our oxygens. What value has to go here? Okay. So now we have a balanced chemical equation. What do you suggest we do now? Solve for moles. What do you want to find moles of? Okay, we're going to find moles of calcium hydroxide, which I just butchered the spelling of. Oh, is that right? It doesn't look right. Yeah. Calcium? Okay, I don't know. Self-conscious about my spelling now that I'm being Zoom. All right. We don't have a way to get grams of this guy, right? So how are we going to find moles? Yeah, molarity. Mole over liters, right? Manipulate that around. What are moles equal to? Yep. Okay, so we can find that, right? We're trying to find moles, calcium hydroxide. Okay, what's the concentration of the calcium hydroxide in this case? Yep. And then what else do we got? Yep.
There's no zero. Oh, just kidding.
I converted it all the way. So if you want to, you can write it out and show the conversion. I tend to normally do that because I'm bad at looking at zeros. Okay, we multiply this through. The result I get 0.4375. Is that our answer? Okay. What are we looking for? Grams of what? Okay, what do you want to do with this thing? What do you want to convert it to? Right. So, what unit's got to go on this denominator? Yep. Up top? Yeah. Numbers. Bottom? Where'd you get that from? Yeah, that's balanced chemical equation. You multiply that through, the result I get is 0.8750 moles of HCl. Okay, what now? Okay, we got to convert this bad boy to grams. can do that pretty easily. 0.8750 moles of this guy. What units got to go on this denominator? Yeah, moles. Up top? Yep. For every 1 mole, anybody know how many grams approximately? Yep. 36 point, what was it? I got 6.1, I think. Yeah, that's okay. Rounding. You do this through, I think I calculated 79, like that doesn't make sense. Multiply, can someone multiply that through for me? Yeah. How did I know that didn't make sense? Yeah, it can't be larger than 36. We're multiplying by a fraction that's less than 1. Okay, so it was 31.9, you said?
Yeah.
Okay, unit?
Grams.
Yeah, there we go. Okay, so this is the first part. Yeah.
It would be four sig figs though, right?
How many? It would be 4 sig figs. So what number should be here?
0.
Yep. So how many sig figs does this value have? That guy? 4. So our original starting numbers right along here, we have 4. So we should be carrying 4 throughout the entirety. If you actually hold more sig figs, it's better, and then determine them at the end. Okay, we got grams. What now? What are we going to find next? Molarity. Okay, and we said molarity is equal to what over what? Yep. Okay, so what are we trying to find the molarity of? Yeah, we're trying to get hydrochloric acid. Okay, so we know how many moles of hydrochloric acid we have. How many moles do we have again? Yep. Okay, and then what is the volume of acid we want to have? Yeah, 50 milliliters, right? Okay, got to convert that from milliliters to liters. 10 to the third milliliters for 1 liter. You multiply that through, what did you get as a result? 50. How many sig figs does this number have? Yep, 4. Remember, those trailing zeros matter. And what is my unit on this guy? Yep. Or you could do moles per liter. Okay. Everybody feel pretty comfortable with that? Okay, know how to do that for the next exam. You'll have a very similar problem. And notice, no M1V1 is equal to M2V2 is used here. Okay? What's the only time you ever use M1V1 is equal to M2V2? Yeah, dilutions. What am I going to do here if you use it any other time? I forget, did I say jump kick or scissor kick? Jump kick? Okay. I've been watching a lot of, what's that one? Cobra Kai. I'm ready, man. Be prepared. Okay, so last time we finished off with chapter 4. We're done with that one. We're actually going to skip ahead a little bit. We're going to move to chapter 10 and talk about gases. The reason for that is it makes chapter 5 a bit easier to explain what's going on, and we're talking a little bit about thermodynamics. So we're going to jump to chapter 10. And that's all about gases. Okay. And how did we define gases like way back when we first started this course? Or how would you describe a gas? What do you know about the distance between the particles in the gas? Yeah, they're far apart. So particles are far apart. What do you know about its shape? What shape will the gas assume? Yeah, Yeah, whatever its container is. Shape of container. What about its volume? Yep, it's indefinite. It'll take the shape, or it'll take the volume of whatever container it's in, right? So indefinite volume. Okay, so let's talk about different properties of gases. If we know these tidbits of information about the gas, we can predict a lot about its behavior. Tell me something that influences the behavior of a gas. Any properties? Yeah. Yep, temperature is a big one. Give it the symbol T. What is the unit commonly associated with temperature? Yep, Kelvin. We'll put unit here, Kelvin. And what is meant by temperature? Yeah. The measure of what? Heat is actually the transfer of thermal energy from one body to another. So it's something else that's a little bit different. It's kinetic energy. It's the average kinetic energy of all the particles that are running into our probe. So a measure of average kinetic energy. Of gas particles. Heat is something else, and we'll talk about heat in the next chapter when we're discussing a little bit about thermodynamics. There is a slight difference there. Give me another property. Will, what do you think? What kind of, got a property in mind? Pressure. Pressure, yeah, big one. Pressure. We're going to give that the symbol. Can you guess? Yeah. Anybody know what unit we're going to be in? Or give me a unit of pressure. There's a bunch of them. What was that? Yep, ATMs. Yep, that's what we're going to keep our units in. ATMs. Does anybody know any other units of pressure? There are a bunch of them. Yeah. PSI. Yep, PSI. You always have to check your car tires and stuff, see what the pressure is. Any other units? Anyone ever heard of a Pascal before? Those are the SI units of pressure, but we often use ATM. Does anybody know how is pressure defined? We're taking a physics class. Pressure is equal to something over something. Anybody know? Yeah. Yep, force over area. And what is the pressure? We'll talk about that in a moment a little bit more, but it's basically like the particles, they're bouncing off the container of whatever they're held in, and that's what the pressure is. It's actually all those little particles hitting there. Early on in science, they had no idea what was causing pressure. It wasn't until they started studying Brownian motion, where you had a little piece of pollen, and you put it in some water and you looked at it, and what would happen is this pollen would jostle around, which is pretty weird. Shouldn't it sit stationary? It's sitting there. And Albert Einstein looked at this and he said, I wonder if it's tiny little itty bitty particles that keep hitting this piece of pollen to cause it to move around. He did some mathematics and he showed that. And from that point, they started thinking about gases that way. And Kelvin, Boltzmann, and a couple other big names of thermodynamics thought of these little particles. It was the first time that they had thought of tiny particles that way. Okay, give me another property, something else. What's going to influence the behavior of a gas? Well, what did we say about its shape? Depends on the container, right? So how do you measure like the amount of a container, I guess? What property are you keeping track of? Yeah, volume. Volume. What symbol do you think we're going to give it? Yeah, not very creative. Unit. Yep, liters. And it's just basically the space occupied by gas. Okay. And last one, really big one, important one in chemistry. What do you think we're going to keep track of? Yeah, moles. So moles, quantity of particles. We give the symbol N, little n, moles, and that's pretty self-explanatory, right? Number of particles. Okay, so let's hop back to this idea of pressure for a moment. We'll play with some balloons, and then after we talk a little bit about pressure and how that's measured, we'll move on to some simple gas laws. Okay, so next section is titled Pressure of a Gas. So a gas exerts pressure on any surface it comes in contact with. Pressure on any surface it comes in contact with. So we look at a balloon. It's going to be really weird to do it through this thing, but we'll try it. We have a balloon here. It is not very impressive right now. Why is it the shape it's in? Like, why isn't it inflated? Yeah, there's no air. There's some air in it, right? We have air floating around right now. But the pressure on the inside is equal to 1 atmosphere, or whatever it is at this point. It's not beating out the atmosphere, right? So why is it hard when you blow up a balloon? Why does it take some like lung power to do it? Yeah. Like everybody's blown up a balloon, right? Want to have an awesome birthday party? Where do you get balloons? We're not 5, but some people still like them. So you have to blow into it, right? What are you fighting against? Yeah. Yeah, because there's pressure all along here. We don't feel it right now, but we're being squished by a ton of particles on top of us. 1 atmosphere of pressure is pushing down on us. So to fight the pressure of it, we have to fight 1 atmosphere of pressure. So we have to blow in more force into this point. So we do that. Okay. So now we have a balloon here. Ooh, it's an ACS balloon too, American Chemical Society. All right. Why does it stay inflated? What's going on the inside of this balloon? Well, what do we have on the inside of the balloon? Yeah, we have gas, right? So there's gas. What's happening is the particles of these balloon, or the particles on the inside of this balloon keep hitting the walls of this balloon. They're fighting against the particles that are smacking on the outside. So which ones would you say are winning right now? The ones on the inside or the ones on the outside of the balloon? The inside. They're pushing back more. That's why they've expanded out further. It might be due to the pressure on the inside of this thing, which is controlled by the number of moles right now. If I squeeze this balloon a little bit, what am I going to do to the pressure? I squeeze it. Is pressure going up or is pressure going down? Yeah, it's increasing, right? Because you can see the walls, they're pushing out that way. If I had you come over and touch it, it would feel a bit harder, right? So, what's happening in this case is you have a wall, the walls of the container. This is our container walls. And the gas particles are ping-ponging, just bouncing off the sides. And that's what the volume of the gas is, in that case of that balloon. All right. So we said, how do we define pressure again? Pressure is equal to what over what? Yep, a force over an area. Okay. And then what's force equal to again? From Newton's laws of motion? Anybody know? Yep, mass times acceleration. So now I'm going to ask a question. What are the SI units of pressure? Okay. So let's hop back to our expression. E is equal to force times an area, right? Okay, what unit do you normally express force in? Okay, newtons, we can do newtons. We have newtons over an area. How would we express that in SI units? What is the SI unit for distance? Meters, right? So what about an area? Not cube, that'd be a volume. Yeah, meters squared. Okay, a newton isn't actually an SI unit, right? It's a conglomeration of a bunch of different SI units. Does anybody know what a newton is in SI units? Thinking back to mass times acceleration. Not grams, what's the unit for mass?
Kilogram.
Yep, kilograms, so kilograms times what? Yep. Divided by meters squared. Let's simplify this. What units are going to cancel out? Or what are we left over with in the end? Yep, so one set of meters is going to go away. We're left over with kilograms, meters times seconds squared, which looks really weird, right? Anybody know what this SI unit is? We mentioned it once. This is equal to a Pascal or a PA. And that's typically the SI unit of pressure. However, it's not a really convenient unit. It tends to be really small. The one we use is an atmosphere. So, a more convenient unit is an atmosphere. Okay, 1 ATM. Talked about that conversion in a second. Remember what an atmosphere is does anybody know what an atmosphere is? Like where do you measure it? There's a special spot on the planet that you have to go to. Yeah, you have to be right at sea level. And then that's the pressure that's pushing down on you at sea level from all the gas particles on top of you being forced down by gravity. 1 atmosphere is equal to 1.01325 times 10 to the second kilopascals. So Pascal is a really small unit. There's another one that's commonly used by meteorologists. It's torr. Anybody know for every 1 ATM how many torr we have? Big Jeopardy question. No? It's 720. This is also equal to another unit. Does anybody know what other unit besides torr you can express pressure in? Another big meteorology one, millimeters of mercury. Torr and millimeters of mercury are the same thing. Now, where does this unit come from? It actually comes from a barometer, how to measure barometers. So we'll talk about those apparatuses in a second. If I gave you guys like some torr, you feel confident that you could convert it to ATM? Let's look at an example. An atmospheric pressure gauge. Reads 728 torr. How many ATM is this? Okay, what are we looking for on the problem? Are we doing on time? We're good on time. What are we looking for? ATM. Yeah, we're looking for ATMs, right? What? Tell me some important information. What's the only bit of useful information here? Yeah. So let's start with that 728 torr. Okay. We're not in the unit we want. What unit's got to go in this denominator? Yep, what's going up top? Yeah. Number, what's going up top? 1. Bottom? 720. Nope. You divide that through, how many sig figs should my answer have?
3.
Yep, it should have 3. 0.958, and what's my unit? Yeah. Okay, pretty simple, right? No craziness, no wizardry, no moles. Everybody feel confident with that? Okay. So, you might see this a lot too. Standard atmospheric pressure. Anybody know what is considered standard atmospheric pressure? Yeah. We shouldn't have. You're right. Oh, I know why, because I'm a dope. Not 720. 760. My bad. Good catch. That should work out now, right?
Does that mean for
What was that?
okay.
Oh, you sure?
Yeah, you already changed it. I didn't know if it changed.
Yeah, I changed it up here. I'm sorry. Got ahead of myself. I'm excited about the demo we're going to do today. We're going to play with some liquid nitrogen. I want to get to that point. Okay, so what's standard atmospheric pressure? In terms of ATMs, what would be the simplest value to pick? Because we could have a different range, right? If you had to pick one pressure to go have everything be based off of, what would it be? How many ATM? 1, yeah, makes all your math simple, right? So we say a standard atmospheric pressure is 1 ATM. So most of the time when you conduct an experiment, you either assume that this is 1 ATM or you set up the laboratory so the pressure is 1 atm. Okay. Now, how do they measure these pressures? There's a handful of different gauges you can use to measure pressures. And they operate in kind of cool fashions. The one that we're going to talk about is a barometer. Does anybody know what a barometer is used for? And what? Yeah, so it's to measure the pressure, the atmospheric pressure. So used to measure atmospheric pressure. Anybody have any idea of how these things work? It comes from this unit of millimeters of mercury. So the way that they used to build these things is they would get a pool and they would fill this thing with mercury. Not very safe, but it's there. Then what they would do is they would get a capillary, a little tube. They would submerge it in the mercury and they would cap the top off. What would happen is as the pressure of the atmosphere pushes down, squeezes down on the sides, what's going to happen to the level of mercury on the inside? Yeah, it's going to oscillate. It's going to go up or down, right? So this difference, this change, let's say it started here, and I don't know, the pressure got higher throughout the day, and we ended up at a new level here. They would measure this in millimeters, hence where millimeters of mercury comes from. So most pressure gauges work this way. They feel a pressure, something pushing down on them, and then they give a result back out.
What is the
P subscript ATM. Like this. P ATM, standing for pressure of the atmosphere. Okay, any questions about that? No? Okay, let's look at some simple gas laws then. So, the people I described, like Boyles, Charles, and Avogadro, they were concerned with these little particles. They weren't sure if gas particles existed or what was causing it, but they looked at these different properties and they came up with what are called equations of state. What an equation of state is if you look at different properties, you have everything you need to know about the system, and you can predict anything you want to know about it. It's really useful, right? Well, they came up with a series of simple gas laws. And there were 3 of them. Can anybody tell me any one of the 3? Just even the name of it. Anything you had to know from high school, maybe? Boyle's law? Does that ring a bell? Anybody know what 2 properties it had to deal with? Well, you got 4 of them, right? Pick 2 of them. Yeah. Temperature and pressure? That is actually Charles' law. We'll get to that one. Give me another one. Yeah, pressure and volume. So, we're going to look at a proportionality. A proportionality is just kind of an idea. You're looking at like what happens. As more people get into the room, it gets hotter, right? We show this with a little Jesus fish. It's not an equal sign, it's a proportionality. Now what happens to pressure? Like if I increase the pressure, so I squeeze on this system, what's happening to my volume? Increasing or decreasing? Decreasing. So would you say that these have a direct proportionality or an inverse proportionality? Inverse, right? As pressure increases, volume decreases. So how would you frame this mathematics? How do they relate to one another? Pressure goes up, what happens to volume? Goes down, right? So we would say we have an inverse proportionality. Pressure goes up, volume goes down. At constant, what properties are we keeping constant in this balloon right now? So I squeeze it. What properties aren't changing? Yeah, temperature, anything else? There is something else because we're a man, but yeah, moles aren't. Okay, if we want to look at the change between two states, so considering change between two states. So before I squeeze it and after I squeeze it. We'd have P1, V1 is equal to P2, V2. How do I get that? We'll explain that in a minute when we look at the ideal gas law. Okay? So we said we have Charles' law too, and what was that one? Yeah, temperature and pressure, right? In this case, let's do temperature and volume. Let's keep it all related to volume. So we have volume, some proportionality. Keep track of this one. We're going to do 2 experiments today. We're going to do one that we can visually see pretty easily. All right, so, I have my gloves. What we're going to do is I have a balloon here. We've all seen the balloon already. We're not going to worry about this thing yet. And I have a metal container. In this metal container, what I'm going to do is I'm going to put liquid nitrogen in there. And then we're going to submerge the balloon in. I'm going to walk around so you can check out the liquid nitrogen. Liquid nitrogen is very cold. Does anybody know what temperature it's approximately at? It's at about 77 Kelvin. Does anybody know what approximately room temperature is in Kelvin? How do you convert from like Celsius to Kelvin? Anybody know? You add 273.15 to it. And what's approximately room temperature in Celsius? Anybody know? Yeah, about 25. So math that for me. What's the temperature approximately of this room? 298.15, right? It's a pretty big difference in temperature. Okay, so we order this stuff. It comes in a dewar, which is way bigger than this, but this is sealed to allow for the temperature. It's vacuum sealed to allow for the temperature to not change very much. What I'm going to do, I'll take this off and you'll see some smoke coming off. That's not dangerous. What it is it's actually water vapor coming off because the system is so cold. What I'm going to do next is dump some of it in here. I'm going to walk around so everybody can check it out. Okay. As it gets everywhere, that was cold. Woo! Okay, and you kind of see stuff hissing and popping around. as I walk around is to look inside this container. Can you see in there? Check it out. What can you see is happening in there? What's it look like? What's it look like it's happening in there? Everybody, let's sneak down this side. Check it out. What's it look like it's doing in there? You see the smoke coming off? Really cold, I gotta move a little bit faster. Sorry. See it in there? What do you notice it's doing? Really cold. What do you think's happening in there? If you feel like it's cold, you can put your hand in it. Yeah. So what do you guys see is happening in there? Yeah, it's bubbling. So what's actually happening to that liquid nitrogen? It's boiling. Like I said, it is harmless. If you go fast enough, there's a property where you can get in there and it won't hurt you. So I can go really fast. It will freeze things though. So let's check out, or like you can see, there's ice actually forming on my gloves here. So let's take our balloon, let's submerge it. What do you think is going to happen to the volume of the container? So actually, if you do it right, you can actually get air to condense on the inside of it. Let it warm back up. Kind of lumpy now, but it'll go back to normal. Warm day, cold day. All the guys in the room definitely get what I'm talking about right now. So you can see the container, it changes shape. Well, let's do another situation. Let's go to this other thing I have here. Let's see what happens to the volume of the gas. We're going to move from 77 Kelvin to a really warm temperature pretty quick. So what I'm going to do is I'm going to dump some of this liquid nitrogen in this vacuum flask. This vacuum flask is designed to hold a lot of pressure. Don't ever do this at home because if you don't have the proper glassware, it won't work out right. I'm going to try and dump some of it in there. Hopefully I don't break this thing. Okay, and what we're going to do is trap the gas. And you can see it's actually like boiling on the inside of there. And we're containing as much of the gas as we can. So what's happening to the volume as the temperature warms up? Is the volume increasing or decreasing? Increasing, right? We'll see. So, holy cow, that was loud in here. Woo! Well, now we're going to get bugged by the campus security, and they're going to be like, what the hell is that? So, the other cool thing, what I normally like to do while we're outside is blow this around. Like we can actually take it and toss it up in the air. You can see that it changes volume pretty quick. What we're going to do, we're going to just, I don't know, I guess we'll just toss it up and hope for the best. All right, you ready? Here we go. So you'll see it hisses, it goes around, there's like smoke going all over the floor. If you're wearing open-toed shoes, don't touch that stuff, but you can see the liquid nitrogen's jostling around and it's bubbling off. It won't hurt anything as long as you don't touch it directly. However, you don't want to touch this pan right now. What temperature is it at right now? Well, yeah, really cold. 77 Kelvin. Okay, so now, that was still really loud. Right? It is. It's a good one. So, we'll let that sit there and try and have that warm up. Did what I said don't do. Good. So, what's the relationship between volume and temperature? Is volume, or is temperature, what's going to happen? If temperature decreases, what do we see happen to the volume of that balloon? Decreases. So, what should the proportionality be? Are they direct or indirect? They're direct. So, should I have a 1 over t here? No, just regular t. Now, let's say I wanted to change between two states. What would the mathematics look like, keeping the inverse one in mind? So what this is showing is this is equal to a constant. We'll call it, I don't know, K2. So let's say I want to change between two states. I have V1, T1, what's that going to be equal to? Oh, actually, no, this is incorrect. That should be a constant, right? Volume over temperature should give us a constant. So if I'm changing between two states, what do we need? V2, T2 is equal to what? Yep, V1 over T1. What do we keep constant in this reaction? At constant what? Yep, at constant pressure. And what else? Yep. A constant pressure in moles. The last simple gas law, that's known as Avogadro's law. So we see the name Avogadro. What do we think that's going to be in relation to? Moles, okay. How do moles in volume, what's their proportionality? If I increase the moles, what happens to the volume? So, we actually had a demonstration of this earlier when I was blowing up that balloon. I was introducing more gas particles into this balloon, right? What happened to the volume as I put more particles in here? Increases. So what should the proportionality be? Yeah, they're direct. So as volume increases, moles will increase at constant what? Temperature and what else? Yep. Okay, and if you want to look at the change between two states, it's going to look almost the same as this guy, right? So we got V1, N1, what's that going to be equal to? Over. Okay, you may have had to know these laws for high school chemistry. I don't want you to memorize these. This eats up too much hard disk space. I forgot the face of my grandmother because I had to remember all this junk. It's not good. What we're going to do next time is we're going to unify all these laws into one grand ideal equation. So too many laws, too many equations. I want to get to one unified law. Or one unified equation. And that's what we're going to do next time. Okay? Are there any questions? Okay, there's a bunch of liquid nitrogen to toss out. What I'm going to do is I'm going to bring it outside and fling it outside. If you want to be a part of that, if you don't, that's okay. Don't forget your daily problems. Any other questions? All right, have an awesome day, guys. Oop.